slide, Rama. And then one of the other things about concrete is the reason I compared it to being human is that concrete is also a live material. Once water comes in contact with cement, the time has started. Yeah. And so once you make concrete, once cement and water come together, we have a limited amount of time within which the concrete will start to change its properties, and we need to be ready for it. Small delays can have a big impact. So it needs a lot of focus and effort once you put cement and water together. Next. Of course, once you make your concrete, you have to place it, and then you can start to finish it. Again, as I said, it's a moldable material. You can make pretty amazing shapes with it and get some amazing properties once it hardens. And if you're doing flooring, which is sort of one of the focus the focus for today's webinar, you can also look at more than just simply finishing it in terms of troweling, edging, and grooving to give a little, let's say, makeup to the concrete in order to make it look good as well. After you place it, you got to make sure that you're curing concrete. I think we all know this. However, curing of concrete has been quite a black box as well, with a lot of practitioners having different opinions on what proper curing mechanisms are. And I have heard different versions of curing. And so, but at the end of the day, it's important that once the concrete is placed, the water consumption changes, whether it's through evaporation, whether it's through chemical reaction within the concrete, the water consumption changes, and the water consumption has some specific impact both on durability and also on later age properties. That's why curing of concrete is a very, very essential, however, sometimes an overlooked step that is necessary for concrete. However, if we do all of this really well, we can have heavy loads that the concrete can hold. Like I said, it's an amazing material, and it's amazing what you can do with concrete today. Next. In terms of bleed water, bleed also has different connotations. Like many things, there's nothing right or wrong about bleed. It depends upon your application. In certain applications, bleed is deliberately done in order to prevent plastic shrinkage cracking, especially under very aggressive wind or heat conditions. Bleed may not be a bad thing. However, if you see bleed in conditions where these aggressive environments are not there, then you may have some issues on the top surface. So again, it's a tool that you have, and you need to be able to use this properly. Otherwise, as I show in the next slide, you could have shrinkage cracking, and bleed can prevent some of those cracking under these aggressive conditions. So those were the first initial slides that I wanted to get our, let's say, appetite growing in terms of just to get to know the basics of concrete. And now let's get into some more details about hydration. What I'm going to talk about will still be very basic for quite a few people who are practitioners. However, this is mainly for those who may not be aware of the chemistry of cement and hydration. So cement hydration is the primary reaction that today helps us make concrete. Without cement today, there is no concrete. However, tomorrow things could be different. Now, cement basically relies on an exothermic reaction of calcium silicates with water. And that's what pretty much gives us the properties that we see in concrete. Calcium silicates and aluminates in the cement react with water to form primarily calcium silicate hydrates. The aluminates, of course, form aluminate phases. One of the very commonly known phase is called ettringite, which is actually one of the first things that you see when you react cement with water. However, over time, you see growth of the um, calcium silicate hydrates over time. And this is ultimately what brings about a lot of the properties that we see both in the plastic state, but more so in the hardened state of concrete. One of the orphans in the chemistry of concrete is calcium hydroxide. Um, it actually has a lot more benefits that one really gives it credit for. It keeps the pH really high. It helps reduce the propensity for corrosion in concrete by passivating the iron rebars. Um, but it also ensures that the CSH formation is happening at a regular basis in order to generate the calcium silicate hydrate, uh, which then becomes the key property of concrete. And typically you get about greater than 50% of the design strength in 72 hours. Next. So then let me take you through some of the kinetics of cement hydration. What actually happens when cement comes in touch with water? So initially, when the cement comes in touch with water, there is an initial period where nothing much is happening. There's a lot of ettringite that starts to form, like I said, pretty immediately. However, none of the CSH hydration starts early. And what happens is there is this period of time, which is a quiet or the sleeping period, which is the phase when a lot of the initial nuclei or very small particles of CSH are being formed. And this is the key step which then allows the next phase, which is the growth of the CSH cluster. Next, Rama. So if you are looking at a cement grain, sorry, if you could go back, Rama. If you look at a cement grain in the initial phase, you will see mostly cement surface, but there will be this small nuclei of CSH shown here in purple, I think. And these are the places where the growth phenomena of CSH starts. And as the hydration continues, these are the points where more and more CSH starts accumulating and growing, and then slowly it grows across the surface, all the way covering the full surface. Now, while this looks sort of interesting, this is also sort of bad in one way, right? Because you cover all of the cement surface pretty early in its hydration reaction. It makes it more difficult for water to enter through the purple CSH surface to get to the yellow cement particles, to hydrate, to dissolve, and bring it back out and precipitate at CSH. So this is why it takes a long time for the concrete to gain its full strength, because the rate of cement hydration starts to slow down quite significantly. Next. And here's a picture, an SEM image of a cement grain in the middle, and you can see the CSH being deposited all around it. And so basically, this is how cement hydration proceeds in order to get to CSH particles, which then allow or give strength properties as well as other properties to concrete. Next. So if you look at the lifetime of what happens in concrete, as soon as you batch the 0 to 3 hours, there are a lot of tools available today to deal with the properties or to maximize the properties at different stages of the lifetime of concrete. So in the initial phase of 0 to 3 hours, you're basically dealing with plastic properties of concrete. Is it easy to mix and form the concrete to make a homogeneous material? Is it easy to hold the homogeneity and the workability level of the material long enough so that you can go and place it properly? is the how difficult is it to move the material, and we'll talk about rheology in one of those slides. So these are properties that today we are able to manipulate with cementitious system and concrete, which allows us to separate the ability of water to give workability uh, out of the workability equation. So today, water is not the main component of getting workability. There are other tools available that can bring these properties while maintaining some of the benefits of water low water to binder systems. Then from 3 to 6 hours, we are talking about the hardening phase. You can either accelerate it or retard it. We have systems, tools that allow us to do that. The 6 to 24 hours is actually a very critical phase for concrete. It's almost like a child. This is the time period where you got to take very good care of your concrete if you want really strong concrete later. This is where all of your initial strength control comes in. Shrinkage related activity starts to happen, which has to be taken care of. And then as you go from 6 hours to 28 days, if you can take care of the concrete during this period, it will reap a lot of good benefits for the rest of its life that you give, whatever it is, 100 years, 50 years, right? After 28 days, there are not a lot of villains in for concrete. You talk about long-term durability, but most of it would be related to external environments. So either external movements, corrosion because of aggressive environments with de-icing salts or seawater ingress, sulfate attack coming from external sources. um, Alkali silica reactivity is the only one that could be more internal in nature, but still requires a source of water to be able to move these ions around within the concrete. Biogenic acid corrosion, typically found in sewers and other systems where sulfuric acid is generated by bacteria. And chemical environments. You could have environments like a chemical storage tank or exposure to chemical cleaning agents where you need to protect your concrete. So these are some of the villains that come in later. But like I said, the 6 hours to 28-day is the most critical part of the lifetime of concrete. This adds a lot of stress, and there are options available today that help mitigate some of these stresses. Next. So today it's amazing what we can do with concrete. 10 years ago, when we were thinking about the structures we build and the kind of challenges we face today are completely different. So whether it is a 200-meter cooling tower or digging a big hole through the ground using a TBM machine, or building an RCC dam of a humongous nature in terms of volume of concrete, you can do wonders with concrete today. Next. And basically, what makes this thing viable are admixtures. So today, being able to do outside of the ordinary with concrete is not imaginable without the use of these chemicals that help manage the properties over the different time scales of concrete. So over the next few slides, I wanted to sort of go through some of the mechanism of how some of these admixtures work. So we have admixtures called dispersants. These are chemicals that basically help disperse cement to give workability, higher workability. These are basically substitutes for water. Yeah, these are the ones that allow us to keep the water low in our mix to get the maximum strength benefit while getting the workability that we need in order to uh, make your concrete and place it or pump it. So next. So the way the admixtures work, and polycarboxylate ethers is one of the key admixtures that is used today in the industry to disperse cement. And the way these works is that cement particles typically are very fine and they like to agglomerate with each other. It's no different than the dust particles you see on top of your table, or on the fan for on the fan, for example, a ceiling fan, or So they like electrostatic areas. They like to agglomerate together because of electrostatic attraction. And what these PC admixtures do is their first job is to go bind to these calcium ions in these cement particles. Next. And once they bind to these cement particles, then they automatically break that electrostatic barrier, but also create a steric barrier, which is a physical wall around the cement particles that pushes other cement particles away, thus de-agglomerating cement. And that's how you get flow in cementitious systems with these admixtures. These admixtures also play a critical role in determining the stickiness or the lack of stickiness in concrete, and I have one slide on that. Next. Polycarboxylate ethers has a huge advantage over other types of dispersants like BNS or lignosulfonate. BNS or lignosulfonate typically, chemically, you can sort of make only one type of molecule. You can't do much with the structure of these molecules. Hence, the performance is pretty similar. However, what the polycarboxylate ether allow you to do is to mix and match different types of chemicals, and you can actually regulate properties in concrete uh, by sort of almost engineering the structure of these molecules. So here in this graph, this was the advent of a methodology by which we learned how to increase workability retention of cementitious systems, where you could basically add on a second component. So for example, you could add the first dispersant to get the flow that you needed, and then you could add a second component either in the same bottle or separately to basically maintain the same workability over a period of time that you want to place your concrete. Because cementitious system by definition will lose workability over time, and that is who they are. That is the character of cementitious system. You want them to lose workability, otherwise they will not gain strength properties. So it is that balance that you strike between how long do you want to work with and when do you want to gain strength in concrete. And this balance can be managed through different chemicals today. Next. Lowering of stickiness in concrete is recently become a more important phenomena, and countries like Japan have already been doing this for a decade now. However, many of the countries, including countries in Europe now, are just learning the benefits of lowering stickiness in concrete. So let me take you through this graph. It will take a little bit of time, so I'm going to go a little slow. So on the graph, on the left-hand side, the x-axis is viscosity in millipascals. On the right-hand side, the x2 axis is slump flow. Okay, and then the y1 and y2, and the x-axis is time in minutes. Okay, and in this experiment, what we are doing is we are comparing the viscosity of or the stickiness of concrete over a period of time. In order to do this experiment, it's very critical that you maintain the workability similarly for both the experiments. Because if the workability is different, it automatically changes the viscosity properties, and then the comparisons may not be valid. So as you can see, with the yellow line and the gray line for these two experiments, one with a normal control PCE and one with a new viscosity reduction kind of a product, you can see that the workability retention from 5 minutes to 180 minutes were held as constant in both cases. And then that allows us to basically look at viscosity over time. And what we see here is that a normal, so if you don't have any PCE in a cementitious mixture, you will still see that your viscosity keeps increasing, okay? So if you do a V funnel of a normal concrete at the same workability, so let's say your workability is 600, 600, 600 over, let's say 3 hours, right? You will still see that the V funnel times will increase for the same workability level over time. And this is not surprising. This is because of a thixotropy buildup that happens in cementitious system over time that increases the inherent viscosity or increases the stickiness in your concrete, even for the same workability level. Yeah. And what I'm showing here is that with these new types of chemicals, so the blue line basically is a typical control polycarboxylate ether type molecule, where you start off with a higher viscosity as shown at 5 minutes in the blue graph, which is about 70 MPas, and it continues to increase over time even though the workability is constant at about 700 flow, right? However, with this new type of rheology enhancing admixture, the increase is minimized. So two things happen. At 5 minutes, you see a drastic reduction in viscosity with these materials, but even over time, the viscosity doesn't change very much. So why is this important? The reason it is important is because while we do all the SCC testing at 5 minutes, we are not placing the concrete or pouring the concrete or pumping the concrete at 5 minutes. We are doing it at 60 or 120 minutes, which means that if we get a nice number at 5 minutes, that doesn't mean that it's going to pump very well at 3 hours. Because of thixotropy, you will see an increase in stickiness. And so this is why the rheology retention is a very important characteristic that helps not only get a concrete of the right viscosity initially, but then it maintains that ability to pump and place over time. Next. So that shows the differential in viscosity over time. Okay, so why is the control of viscosity important? This is something I don't have to explain to a lot of practitioners. Buildings are getting taller and taller. We have a Kingdom Tower now being constructed, which is a kilometer high. And pumping becomes a critical characteristic with typically single stage pumps where you have to pump pretty high. And so reduction of viscosity becomes a very important parameter, especially for a higher grade concrete where stickiness is often observed. Or it can be a Myvan type of formwork, which doesn't allow you a lot of space to actually place the concrete easily. And again, it's important that while you're placing the concrete after 1 hour or 2 hours, the concrete rheology properties, despite the thixotropy increase, is compensated by these molecules. Then it makes the pouring experience much better. Or for pumping concrete long distance, which has a whole range of other challenges, however, can be done by reducing, again, the viscosity of concrete. Lower viscosity of concrete can also give you better surface in general after you strip off your formwork. Next. The next, this slide basically tries to address this issue of strength development and to accelerate strength development. Now, one thing that one needs to understand in terms of mechanism is that a lot of the setting time and strength development properties are a little different, right? When you're talking about setting time, you're primarily talking about ettringite growth. And this is what controls most of the setting properties over time. And the strength development is governed mainly by the CSH formation and growth properties. So if you want to accelerate set, you can use chemicals that will accelerate ettringite formation. If you want to accelerate strength, you need other chemicals that will actually help a quick or an increased rate of growth of CSH particles. So next, so on this slide, I wanted to compare, Rama, can you go back? Sorry about that. So on this slide, I just wanted to show you two images, again, cryo-SEM images, where we were studying the growth of CSH particles around the cement particles, which you can see on these two images. On the image on the left, the blank areas are basically what the cement particle is. You don't see a lot of CSH formation yet on that surface, right? It seems pretty bare. And you can see some hexagonal crystals there. And those are the ettringite, which are formed right away. On the top right is a cement surface at the same age, but using a strength accelerator. And you can see that you can see more CSH being formed all around the cement particle, which is in the middle here, there in gray. And like I said, you can induce higher CSH generation using these chemical nuclei to get very early age strengths. Next. So the next topic that I wanted to address on this slide about concrete, which is again a big villain, is clay in manufactured sand or in river sand as well. Clays are ubiquitous in nature. It's found everywhere. And clay in sand can wreak havoc in terms of concrete properties, both in terms of plastic and also in terms of hardened properties. And while there are different kinds of clays, the expandable clays like cementite are the major problems that one need to worry about. And these cementite clay can increase surface area very significantly. And more surface area means that all of the chemicals that we are adding into the concrete are getting preferentially eaten up by these surface areas by clay, which means you're not going to see a lot of changes happening in the concrete itself, in the cement grains itself. And often what this means is that your dosage of chemicals goes up high to get any kind of desired plastic properties. This could also result in very rapid workability loss, again, because of absorption of a lot of chemicals by these surfaces. And because of absorption of high amounts of water, these can also cause plastic shrinkage cracks when you have high amounts of clay. Next. So here was a experiment that I did when I was in India to try to characterize what kind of clay we have. So we picked up sand from Shanghai, Mumbai, and Malaysia. Malaysia won this battle. It has the highest amount of expandable clays. The MBV value or the methylene blue value is one of the way to determine how bad your sand is in terms of clay. But it doesn't tell you how much of that is expandable clay, because methylene blue value will give you a response to most clays. To understand whether you have expanding clays, you need to do an experiment called X-ray diffraction, where you basically put a material to force the clay to separate out, and the blue and the yellow line tells you whether the clay platelets have separated. So in the Shanghai sand, for example, there isn't a lot of expandable clay, because even when you add a small amount of chemical, it doesn't separate out. That means these are not platelet types materials. Whereas in the India sand, and more so in the Malaysian sand, you can see these peaks separating out, which means that the clay is actually expanding. And the degree of expansion is basically the differential between those peaks. Next. So some of the issues that you would face with clays and sand include higher dosage of chemicals. You could have fast loss in workability to the point that your concrete will look like mud over time. And fluctuating dosage and stickiness. Your stickiness will increase significantly, as well as your plastic shrinkage, cracking potential goes up significantly. Next. The last part of my presentation, I want to focus mostly on cracks in concrete, which are a nuisance. Next. So let's start with plastic shrinkage cracks. There are three major types of shrinkage related cracks that we would see in concrete. One is the plastic shrinkage crack. But before I start, I want to sort of make it very clear that all shrinkages happen because of movement of water. This is the primary reason. There's no other reason. Most shrinkages or all shrinkages in concrete are happening because of movement of water. Plastic shrinkage happens because of movement of water out of the concrete into the atmosphere, also called evaporation. And you can see that in soil, in the image that I have shown. You can see that in your clothes when you dry it outside in the sun, they become wrinkled, right? और अगर आपका 1,000 रुपए का नोट अगर पानी में गिर गया और उसको सिखा रहे हो वो भी सिकुड़ता है. So those are all examples of plastic shrinkage coming from evaporation of water from the substrate. There are three primary factors that affect it. The relative humidity. So if you have a high humidity environment, obviously the evaporation rate is decreased. If your concrete temperature is very high, the evaporation rate is increased. And if it's combining with a wind velocity, you're constructing in a wind tunnel area, then this effect is seriously exaggerated. And this nomograph is available, and Piyush will talk about it in his presentation as well, as to how this nomograph can be used to understand the rate of evaporation and therefore the propensity of plastic shrinkage. Next. So if we want to understand what is really happening, the little cartoon on the bottom left shows the timeline of concrete hardening, right? So you first have workable concrete, then you have concrete setting, and then you have hardening, right? Next, Rama. So if you start to go along that path, yeah, so the red line is the stress level in concrete, right? So as the water starts to evaporate, so nothing much happens in workable concrete, right? Because it still moves around, so it's not a problem. As the concrete starts to set, it becomes harder, right? Then the flexibility is lost quite considerably. And then that is when your plastic shrinkage property becomes very significant. But just because something has plastic shrinkage doesn't mean that you're going to get cracks. All materials have plastic shrinkage. You cannot stop it because the water has to go out. However, what is critical, and next, Rama, is that is the stress generated by the plastic shrinkage, is that stress higher than the tensile stress that your concrete can take at that age? So obviously when the concrete is very new, it has not built up that kind of strength, the propensity of cracking is higher, right? However, and that's where the plastic shrinkage stresses come in. They are not big stresses, but the stress is enough that because the concrete has not built up enough tensile strength by then, you see a crack. Next, Rama. So as the red line crosses the blue line, which is the strength development, when the stress is higher than the strength, that is the point where you will have a crack. If you are always under the blue line, where the stress at any point is lower than the strength gain of your concrete over time, you will still have plastic shrinkage, but you will not have cracks. Next. So this is a classical ASTMC 1579 test where you can use to detect or to measure plastic shrinkage cracking or look at the propensity of plastic shrinkage cracking. This is actually a very exaggerated test that includes a temperature control, humidity control, as well as a fan speed, a wind speed that is artificially built in to exaggerate this effect. But again, there are additives that can help prevent this plastic shrinkage cracking. And you would see these kinds of cracks mainly in elements that have a high surface area, like a slab, for example, or a floor. And hence, you will hear more from Piyush on this. Next. Drying shrinkage is the second type of shrinkage. And autogenous shrinkage is also becoming more and more relevant because people are starting to realize. And these kinds of shrinkage happen when you are starting to go to higher grades of concrete. Because in this case, your water is low enough that there is no worry about plastic shrinkage cracking. Your bigger problem are these chemical and autogenous shrinkage and drying shrinkage. So the best way to look at drying shrinkage is if you look at a sealed specimen versus an unsealed specimen and measure the differential shrinkage, that's pretty much what drying shrinkage means. Next. Next, Rama. So the drying shrinkage happens pretty much around 24 to 28 to 30 days. That's the area to look out for. Anything about 28 days is when you look out for this kind of stress. Like I said, if the stress is higher than the strength, next trauma, if the stress is higher than the strength, only then you get a crack. But in this case, the concrete has already hardened, right? We're talking about 28 days. So imagine the level of the stress that needs to come through in order to get the cracks, right? So the stress level has to be really high to overcome the strength that the concrete has already gained over 28 days, which means when the cracks are formed at 28 days due to drying shrinkage, those are big cracks, those are deep cracks. The plastic shrinkage cracks are most likely on the surface, they are mostly non-structural. These ones could be the dangerous ones to look out for. Next. The cracking potential can also be measured using ASTM-C 1581, which is basically also called as the ring test. So you have a ring which is under stress because of the metal piece inside, and then you're measuring the strain over time under constant humidity and temperature condition, looking for the propensity for the particular concrete material or design to crack. And the blue line that you see is the release of the strain. So as soon as the concrete cracks, it's actually a stress release mechanism, and you will immediately see the release in terms of the blue line. For the other concrete, which has shrinkage reducing agent in there, uh, the crack has not happened, mainly because the stress buildup is being mitigated by the shrinkage reducing agent. Next. So this is just to give you a visual of the different shrinkage test methods. The 1579 is for plastic shrinkage. That is the setup in the middle with the polycarbonate specimens, a polycarbonate enclosure with the concrete specimen that you see, and a bin for water to manage humidity. It's also got a little fan if you look closely. On the left-hand side is the ring test, which is 1581. The 1689 is an autogenous shrinkage method, where you fill the plastic concrete and you can measure the changes either using a laser method or a normal length monitoring method. And the ASTM 157 is the drying shrinkage measurement method shown on the top right with that prism specimen. And this is the most standard method for doing drying shrinkage. Next. So, in summary, again, like I said, I wanted to keep it very basic, but also perhaps bring in a few other nuances. But having said all this, I mean, the one thing we all agree is concrete is the most sustainable building material available today. Concrete is moldable, provides great strength to structures. There are tools available to improve or mitigate most of the issues we have with concrete today. Concrete does need a lot of attention during that early life. 6 hours to 28 days. In fact, 6 hours to 3 days, or 3 to 6 days, right? So maybe 6 hours to 7 days. This is actually the most critical period. You take care of your concrete during this period, you are good to go for the lifetime of the concrete. Then you need to only worry about the durability against external factors, like an external environment, movement, um, um, uh, de-icing salts, like I said, marine environment, high sulfate on the ground, so on and so forth. Next. So I started with Bollywood. I would like to end with Bollywood. So there are many villains that can stress your concrete, right? But if we take care of the concrete during the early phase, the concrete can prevail over all these villains. So with that, I would like to stop here, and I would like to hand it over to my colleague here for this webinar, Mr. Piyush. Piyush, let me quickly introduce Piyush. I look at all the villains smiling at him. Piyush is a graduate from IIT Chennai, IIT Madras. He's a civil engineer. And then after his BE in IIT Madras, he decided to go to the beaches of California, UC Berkeley, and earn his master's degree there. Uh, he's one of those few people who returned back to India, and he has a family business where he lays world-class floors since 2013 across India. Piyush, all yours.
Thank you, Dr. Vish, for the wonderful introduction and the really nice presentation. We are honored to have you here today with us. And I'll just try to load my presentation up on the screen. So, Rama, is my presentation online now?
Clear.
All right. Thank you. Thank you. I'll start my presentation now. Once again, thank you, Dr. Vish, for the introduction and the wonderful presentation. You gave us a very nice overview of concrete from the perspective of a technologist. And before I start my presentation, I would like to thank our great audience here. We got very good response in the first webinar, and we are really humbled. We were flooded by questions, and hope we'll be able to do justice in this presentation also. So I'll be talking as a practitioner. When I say as a practitioner, I mean as a flooring contractor. I would like to go with you over some practical aspects of concrete and how we look at concrete at site. All right, so my presentation is basically structured into broad parts. First is the background. I talk about the perspectives of a technologist and a practitioner. I talk about my experience as a concrete practitioner, and I'll put forward a concrete specification that works for me and in general for the application of flooring. In the second part, that I think is the most interesting part of this presentation is I put you in my shoes. I use some real world data. I use some actual data from one of our sites that we did recently, and put you in the position of a decision maker. Like if you were in my place, what would you have done given the situation? And through this case study, I'll talk about slump, finishing window, and bleed. All right, so we look at some background. This is an image most of us must be familiar with. Basically, two guys, two blind men grappling with an elephant, trying to understand what this is. So, the guy who holds the trunk thinks of it as a snake, and the guy who holds the tail thinks of it as a rope. And unfortunately, this is how we look at flooring concrete. Also, with our limited knowledge, we try to understand what it is, but really it need not be so difficult. Only if all of us, either the practitioners or the technologists, take time to understand, really understand the process, like what the process of flooring is. It need not be like this. It need not be this elephant that we grapple with. So, what I'm trying to say is we need a holistic approach. There are multiple factors that need to be taken into account. The practitioner needs to get into a technologist's shoes, and a technologist needs to get into a practitioner's shoes. Now, what do I mean by a technologist and a practitioner? All right, so a concrete technologist is a visionary, is something that is someone who's always making things better, is setting goals for people like me, always looking for solutions that are more efficient, cost effective. He is well versed with theory, very comfortable with best practices. On the other hand, we have the concrete practitioner who understands site conditions very well, who understands user requirements very well, but he has a job to do. He is dealing with real world problems. He has practical constraints to deal with. He needs something that works, that makes his business sustainable. Why am I putting forward this quadrant to you is we need to consider the view of the technologist as well as the practitioner when coming up with a solution for concrete and specifically for flooring concrete, because it genuinely is unique in terms of requirements. All right, this is my experience. Our company has been building floors since 2012. We have worked across 12 states in India. We have worked in varying weather conditions. This is very important to mention because concrete is very sensitive to temperature, humidity, and all those kind of variables, which Dr. Vish nicely covered in his presentation. We have dealt with erratic raw material quality. Uh, this is a major factor. Like, we do not have a standard solution that we can apply to our different sites. Each site needs to be dealt with independently, and each site is unique. And we have successfully delivered projects in challenging conditions. I would like to add here that we do a lot of warehouse floors, which are 24 by 7 operations. The floors get a fair bit of pounding, and I'm happy to tell you that those floors are standing tall, working very well, and we've handled more than 1 lakh cubic meter of concrete till date. For listeners outside of India, that is about 100,000 cubic meters of concrete. I personally have spent a lot of time on sites and got hands-on experience. So what I'm trying to tell you here is I have learned about concrete from direct experience. I am a civil engineer by education, but my experience has been much more valuable in learning specifically about floor concrete. All right. So, what are some of the challenges that we face? And I don't talk here just about myself. I talk about the whole flooring fraternity, other contractors, other vendors, or anybody who is associated with the industrial flooring. First is hot weather conditions, especially in India. What it does is the concrete sets faster. You have more evaporation, or what it means for me as a flooring contractor is I have lesser time to finish. There is extreme variation in raw material quality across country. As Dr. Vish in his presentation talked about sand across different countries, I would like to add here that within India we have a lot of variation in sand. And forget about different cities. If I'm doing a project and taking my concrete from one specific plant, if they change the source of the sand, my concrete changes completely because the admixture behaves in a completely different manner. And add to this, I would be honest about this, flooring concrete really has not caught the RMC suppliers' attention because each project that we do, we have to sit down with them and explain them our requirements. That is where I feel the gap between a technologist and a practitioner. What we need as flooring guys is not very clear to the concrete suppliers in general. I'll talk about our requirements soon. And coming to the micro level, the site conditions are far from ideal. We talk about best practices, but in very few cases do we ever get what we desire at site. One example would be, uh, so flooring needs to be done in a closed envelope. we do not get our ideal closed envelope. The supply rate is erratic. The concrete supply can vary anywhere from 10 cubic meter per hour to 24 cubic meter per hour. I will go in fair bit of detail on this topic. The concrete quality can be inconsistent. When I say inconsistent, I mean variation in slump within a day, not over days. Also, those who attended the first webinar, I used the slide there as well. I'm just using it for the benefit of new attendees, and it's a good revision, anyways. So, the first process in flooring is we pour concrete in the panel, and the guys spread it to a rough level. The second step is what we use a laser screed. What you're seeing in picture is a boom laser screed. People use truss screed, people use screed vibrators. There are different equipments. The purpose is to level the concrete. The third photograph shows certain tools that we use, something like a bull float or a bump cutter, uh, to suppress the steel fibers or the stone or the aggregate. And when the floor is ready to be finished, we float it and spread hardener over it, a dry shake hardener. What you see in picture number 5 is advanced stage of finishing, where we are panning and uh, using pans on a ride-on trowel. And sixth and the final picture is where you're actually using blades or and troweling the floor to a final finish. I'll come back to this slide right at the end of the presentation and talk more about it. All right, so what sort of concrete do I need as a flooring contractor? I'm very clear about these requirements. In terms of strength, I usually specify an M30 concrete for 2 reasons. First is client's load requirement. We're talking about high racking warehouses where the load requirements are pretty stringent, high. Secondly, as a floor finisher, I need adequate paste for finishing, and a higher cement content provides me that. In terms of slump, I need a slump of about 150 plus minus 25 mm. This is governed by workability and machine requirements and segregation. What I mean by that is, at the lower end of 125 mm, that is the limit of the equipment, and that is also the limit of the comfort of men who are handling concrete, because there is a lot of work that needs to be done. At the higher end, 175 mm is where I'm concerned, start getting concerned about segregation. Beyond that, I expect segregation, so I do not want to go above 175 mm. My third parameter is the finishing window. I need a 5-hour finishing window. So how I define finishing window is the time between the moment you pour the concrete into the panel to the time you start applying the hardener. That is, in a sense, the when you start your finishing process. So I need about a 5-hour gap, because I need my operations to run in a very controlled manner, and I also need to allow for contingencies like delay in arrival of trucks, some breakdown at plant. I will talk about all this in much detail. And fourth is bleed water. I need limited amount of bleed water. I do not want excessive bleed, and I also do not want no bleed. So why do I need bleed? For 2 reasons: hardener application and plastic shrinkage. Dr. Wish talked about plastic shrinkage in a fairly detailed manner. And then there are more parameters. I'm not talking about everything here. I'm just here to give you an idea of how a flooring contractor thinks. All right, so this is now the second part of my presentation, where we look at actual data from one of our sites. I will put forward 3 variables, and I will define my process flow, like how I want how my process of flooring is, and then I will propose a solution given the variables and the process. All right, so my first variable here is variation in batching speed. So if you look at the graph, the x-axis is the truck number and the y-axis is the time. I would want you to focus right now on the green graph. Please ignore the red one for a moment. So if you see, we started batching at 5 a.m. and we ended batching at 8:30 a.m. We had about 11 trucks coming in one after the other. So day 1 went smoothly. Now you look at day 2, that is the red line. So what happened is, we started batching 1 hour late. For whatever reasons at the batching plant, we instructed them to start at 5 a.m. sharp. All right, for whatever reasons, that did not happen. So even if it started an hour late, it should have ended by 9:30 a.m. It did not. It went up till 12 noon. So what implications does this have on me as a flooring contractor? First thing I would like to highlight here is, so the average speed, concrete speed on day one was 19 cubic meters per hour. Day two was 11 cubic meters per hour. It's almost half. So the risk that I am running is cold joints, higher evaporation because 12 noon is much hotter than 8:30 a.m. and my manpower cycle is disrupted. Like they are just sitting there, and then they go back late, and there's a question mark on will they be able to turn back to site on the second day and on the third day and pour or not. So this is one. I would not get into the reasons why day two was different from day one. All I'm trying to say is it happens, and we need to be prepared for this. Now, the story of day two did not just end here. It there is more to it. That is, I'll show that in the second slide. All right. So the red line is what you already saw. That is the batching. And now look at the orange line. Orange line actually tells us the arrival of trucks at site. I will deconstruct this for you. Now look at truck number 1 and 2. They came to the site at the same time, even though they were batched at different times. Second, look at truck numbers 4 and 5. Truck number 4 was batched before truck number 5, but it came to the site after truck number 5. Look at truck number 7, 8, and 9. They all came to the site at almost the same time. Now, what implications does this have to me as a flooring contractor? It's obvious. Some of the trucks would lose slump because they are coming much later to the site than planned, and my manpower cycle is obviously disrupted again. And the third and the final variable is evaporation. On the right is a nomograph published by the American Concrete Institute. Dr. Wish also talked about this. I won't go into the calculations, but I have assumed an air temperature of 30 degrees Celsius, concrete temperature of 27 degrees Celsius, relative humidity of 40%, and wind speed of 8 kilometers per hour. What it means is my evaporation rate is about half a liter per square meter per hour. And I would like to remind you that it takes at least about 5 hours for the finishing to start, and give and take an hour for the transit time. So we're looking at 5 or 6 hour time period where there's evaporation happening in the concrete. That is the least I'm talking about. So what it means is there's a loss of water of 16 to 20 liters per cubic meter in a period of 5 hours. So the message here is, like slump, the effective water binder ratio also reduces with time. The water binder ratio is not a fixed number, it is dynamic. All right, so I have thrown three variables at you: batching speed, variation in batching speed, variation in arrival of trucks on site, and evaporation. And now I will talk about my process, how I work as a flooring contractor. So at time T0, you batch at the plant. It takes about 45 minutes for the truck to arrive on site. You take another 15 minutes to empty the truck. You take a further 15 minutes to level the concrete. So since the time the concrete was batched and you leveled it using a laser screed, it took you about 1 hour and 15 minutes. Then there is a gap of about 5 hours where the concrete just sits there, and slowly it is hardening, it is setting to be able to come to a position where we can actually walk on it and finish it. So we do our first float at about 6 hours. We spread the hardener. It takes us about 15 minutes to spread the hardener. We do a second float that takes us about 15 minutes, and the whole process takes about 10 to 12 hours. So the message here is, we work on this concrete for a period of about 10 to 12 hours, and there are several steps involved, and these steps have a set sequence. One step comes after the other. We cannot mess around with this sequence. And if you're following Dr. Wish's presentation, he mentioned about the moment the cement and water come in contact, the clock starts ticking. That is what I'm telling you here. There's only a set amount of time that the concrete is alive for in wet stage. So we have to be able to handle concrete and deliver the flow that we have committed to the client in that period itself. So timing is very crucial for me. So what it means, so I showed you the flow for just one truck, and this is how it is for each truck. So typically we have about 10, 12 to 15 truckloads uh, per day on an average site. So each truckload should tie into the next truckload without any cold joints. What I'm saying is the trucks should keep flowing to the site one after the other without any significant gap. So being on schedule with consistent concrete is vital. Again, when I say consistent concrete, I mean I need similar kind of slump for all the trucks because it affects my finishing drastically if the slump varies from batch to batch. I think it is pretty obvious that small deviation in any step impacts the whole process. Okay, so now I will come to the solution. Like if I have to make this whole thing work, what should my concrete look like? All right, so first thing that you do is make conservative assumptions. Be realistic about transit time. Be aware that you can have trucks backing up. Be aware that the drivers, even though this is the day and age of GPS and everybody has smartphones, everybody has maps on their smartphones, they might just decide to have a pit stop, have a cup of tea or breakfast. Take all this into account and then design the concrete for a 150 slump at site. Now, what this does is it gives you a cushion of about 25 So let's say for whatever reasons, for delays, gaps in the trucks, your slump drops to about 125 You can still use that concrete because that is your lower end. But be sure to reject loads below 125 because the concrete guy would just dump this concrete and leave, but you're the guy who have to deal with it and finish it. The liability is yours the moment he has dumped it in the panel. So you have to be very careful about your contract with the concrete supplier. Design the concrete for a finishing window of 4 to 5 hours, and you need to choose the right admixture to do this. Again, when I say finishing window, I need a gap. I need this gap between pouring and start of finishing so that I can run my operation seamlessly. You definitely need to insist on a strict schedule of supply. All right, so there's in the first webinar we got a lot of interest on bleed, so I've kind of tried to go in more detail here. So I'll try, and Dr. Vish also spend a lot of time on this topic. So what is bleed? Bleed is nothing but rise of free water to the surface due to the settlement of denser solids like cement and stone. So it is obvious, but it is important to state here that in a concrete mix, the density of water is the lowest among all components, so it is natural for it to rise up. And not just water cement ratio, but the type of cement and also the type of fine aggregate and percentage of fine aggregate determine bleed rate. It is obvious that a higher water cement ratio leads to more bleeding, and the more fines you have in the mix, the lesser the bleeding will be. The photograph shows you bleed. If you look, you can see a little shimmer on the floor. That is the water that has come and sat on top. Hardener also needs bleed. Rama is going to talk in fair detail about hardener in his presentation, so I'll just touch upon it briefly. Hardener is nothing but a mix of stone and cement and some dispersants in a dry form. So when we apply hardener on the floor, we need to wet it. And the way we wet it is we use concrete's own bleed to wet the hardener. So in the photograph, you can see two shades of gray. The darker shade is one that has already been organically wetted by the bleed from the concrete. The lighter gray is still absorbing water from the surface. Okay, so some numbers won't hurt here to bring home the impact of plastic shrinkage specific to floors. So I have so the figure on the left is a cuboid, or for our purposes is a section of a floor about 6 inches thick. On the right side is a cylinder, or for our purposes is a column. What I have done here is I've controlled for the volume. What I mean is the volume of both these geometrical shapes is the same. And now I calculate the ratio of the top surface area to the volume. When I say top surface area, for a floor it is very obvious, and for a column you have shuttered when you're casting a column, you shuttered all the sides. The only place where it can bleed or have plastic shrinkage is the top opening. So just look at the ratios. It is mind-boggling. The top surface area to volume ratio of a floor is 6.67. The top surface area to volume ratio of a column is 0.33. So the ratio of floor is 20 times more than that of a column. So The evaporation is phenomenal in a floor compared to a structure like a column. So I summarize it here. Flooring has a very high surface area to volume, so evaporation is significantly higher, and consequently the possibility of plastic shrinkage. Hence, we definitely need some amount of bleed as a protection against this. I would like to add here there are other ways of handling plastic shrinkage. Dr. Vish mentioned about certain additives. You can use glass fibers, you can use synthetic fibers. They also aid in controlling plastic shrinkage. All right. So, how do you manage bleed water? It is important to note my title. It says managing. It does not say avoiding. While Dr. Vish was giving his presentation, I was looking at the questions, and a lot of people asked, "How can we avoid bleed?" So, it is very important to note that we do not want to avoid bleed. We want some amount of bleed. Now, this is what a technologist thinks about bleed. The water cement ratio of the structure decreases, obviously, because the water comes up on the surface and evaporates. Therefore, the capillary porosity decreases, hence, the density and durability increases. So, in a sense, the technologist is saying bleed is uh, not a bad thing. In fact, it is good for floors. It might help decrease your water cement ratio, decrease your capillaries, and increase the density and durability. Now, let us see what a practitioner thinks about bleed. For a practitioner, it is the first use is obvious. It helps in reducing plastic shrinkage cracks. What he is very careful about is he begins finishing only after most of the bleed water has evaporated. Otherwise, if he doesn't take care of this, it may result in surface defects or delamination. So, this is what I'm trying to convey in this presentation. A practitioner must talk to a technologist and vice versa. A technologist must talk to a practitioner to understand both their views and come to a solution that works in the end to lay a good floor, because that is what matters. All right, as I said, I will bring this slide up again. I hope you would have become more sensitive to the fact that our operation is a very controlled operation. It needs a certain time, and each of these sub operations have a fixed window. Like each of these sub steps need to be done in a certain time frame. If you miss that time frame, you will have problems in the floor. So in a sense, laying a floor is not very much different from an assembly line or a factory setup where your raw material comes precisely at the time you want it to come. You follow a set procedure to do what you want to do. All right, so I'm almost at the end of my presentation. Now, putting it all together again, I will show you some data from one of our projects. So I'm not sure if you can see this, but I'll verbalize it. So this was M30 concrete that we used. The slump at batching, sorry, was 160 mm. The third picture states the water cement ratio. The water cement ratio was 0.47. I'll just summarize it here. So M30.47 water cement ratio, slump at plant 160 mm, slump at site 140 mm. And how did the concrete look like? It was cohesive. We did not have any segregation at site. There was no excessive bleeding. So we are used to handling these kind of mixes. This is what we want actually. This is something that we are very comfortable dealing with. In the last webinar, a lot of people have concerns. If you have higher workability, are you compromising on the strength and all that? No, this is a proof right here, and this is how we work. Basically, this is our standard procedure. And the best part is this specific floor is being certified to be an FM2 floor. So if we get the kind of concrete we need, we can consistently deliver FM2 floors. And this actually is a picture of the same site. I think the pictures tells the story, but if you do take your decisions at the right time and things go as planned, this is what you can expect as a result. And as a flooring contractor, it gives me a huge amount of satisfaction when we are able to deliver floors like these to our clients. So in conclusion, most important views of both the technologist and the practitioner need to be considered to arrive at a solution. We need high slump, cohesive concrete for flooring. We need it consistently and strictly on schedule. We definitely need to take into account evaporation of water, and sufficient bleed water is essential to prevent surface defects like plastic shrinkage, delamination, etc. I've just left a link here. If any of you are interested in reading more about bleeding, you're welcome to just click on this link. Thank you for your patience and time. That's all from me. Rama, I'm done.
Yeah, thank you very much, Piyush. And yeah, I can now start straight away.
Wait, give me a moment. I'm sorry. I would like to take a moment here to introduce Rama. Ramakrishnan has completed his MTech in Construction Technology and Management from IIT Delhi. He has over 12 years of experience and has previously worked with BASF, Ultratech, and Beckert in technical, marketing, as well as sales functions. Currently, he's with Monoflor. He's been there with Monoflor for over 2 years now. He's in the position of general manager and handles Monoflor's business in India. Ramakrishnan is a concrete technologist by profession and passion. I know that for a fact. Over to you, Rama.
Thank you, Piyush, and thank you, Dr. Vish, for setting up the stage for me. Now I will start talking about the other materials that are used for flooring construction that are as the agenda will look like this. First, we talk about concrete reinforcement, and then slip membranes, then hardeners, cementitious hardeners, that is, and then we go on to end the session with sealants. In concrete reinforcement, we'll cover about different types of concrete reinforcement that are present, that are available for use in floors, including steel rebar, weld mesh, steel fiber, synthetic fiber, and we will also try to compare different types of fibers and their application and so on. Just before we enter the topic of reinforcement, just to capture some few questions that have been raised during the first webinar, where the reinforcement should be placed, whether it's top, bottom, or center. Is there a scientific method to get a suitable mix for steel fiber or any fiber, and so on and so forth. We'll cover these topics in detail as we move along. First, to start the topic of reinforcement, I wanted to talk about steel reinforcement first. That is the conventional rebar reinforcement first. So it's typically used in one or two layers, either at the top or at the bottom, or both top and bottom. That are the two layers. You may choose to use either one of them, or you may choose to use both of them, but you need to use any one layer or both layers, understanding what is the significance of it. The top mesh that you're always using is always for shrinkage. If you're using a top mat, it is the purpose of using this top mat is to cover for shrinkage. And then if you're using a bottom mat, it is for movement. So it's very important to understand this. It is not replaceable. If you are deciding to use one layer of reinforcement, you need to understand if it's at the top, you are adding only a shrinkage reinforcement. You're not adding a moment reinforcement. So when you have only one layer of reinforcement at the bottom, it means you're taking care of the shrinkage by good detailing practices. And you are choosing to avoid the shrinkage reinforcement that has to have been at the top. And moreover, when there is a question about minimum reinforcement in any standard is a fundamental property of concrete. This comes from shrinkage of concrete. Minimum reinforcement, if somebody has to use just one layer that is a minimum reinforcement, then that reinforcement is of course at the top. So this is very clear. Now let's talk about the difference between conventional reinforcement and steel fiber reinforcement, which is also another alternative. Conventional reinforcement is of course continuous reinforcement and a layer at a particular level, but whereas the steel fiber is reinforcement at different throughout the section and reinforcement everywhere. The impact and fatigue resistance in a steel fiber reinforced concrete floor is usually much better. There is, of course, the added benefit of construction time saving that comes along with steel fiber. Now, moving on to choosing steel fiber, let's talk about how we choose from different types of steel fibers. The steel fibers have to aid easy mixing, easy dosing, and good performance. Performance is usually characterized of a steel fiber by a length to diameter ratio that's called the aspect ratio. And any fiber that provides consistent performance with a very high network is preferred over a fiber that has reduced network capabilities. Just to summarize different types of fibers and how they are relevant to different applications, it has to be noted that microsynthetic fiber is only a secondary reinforcement that's used for shrinkage cracks. That's also mostly in the plastic state. Macrosynthetic fiber can be used for similar applications. It can be used as a fiber, as a replacement to rebar with careful testing of the ductility contribution of these fibers. Steel fibers, of course, can replace conventional reinforcement in most of the flooring applications. Let's talk about the second material that we were scheduled to talk about, that's slip membrane. Many times there are a lot of misconceptions when it comes to slip membranes. Slip membranes are simply the plastic sheet layer that go on top of the subbase, just below the layer of the final concrete layer, that is the final floor concrete. Virgin LDPE is the most important aspect when it comes to choosing these slip membranes. HDPE may sometimes provide a kind of an advantage when it comes to the contribution that it has to vapor barrier, but it may not always be advantageous when it comes to laying them and taking advantage of the slip membrane performance when it comes to HDPE. It's preferred to have at least one layer, and this one layer has to be just below the floor. Whether it's a subbase, whether it's a lean concrete or a PCC, it has to be, a plastic sheet has to be added just below the concrete layer. Yeah? And when you go for a jointless floor or any floor that has that is expected to have a high amount of shrinkage, you typically like to have at least one layer or maybe even two layers of reinforcement when it comes to adding reinforcement, the number of layers. Preferably, the usual typical specification is about 200 microns of LDPE sheet that's used as an LDPE, as a slip membrane. All slip membranes are not vapor barriers. Vapor barriers are to be specified using the specific property that is achieved using LDPE, using HDPE, or the performance properties that are usually specified for vapor barriers. The bottom line is all vapor barriers, all slip membranes are not vapor barriers. Moving on to the third material that we want to talk about, the hardeners. If this is your concrete floor, you would always see that there are continuous movements that are happening on the concrete floor. So it's always important to design an industrial floor not just for the load that's coming on the floor, but also for the abrasion. If you want to understand abrasion is just as good as scratching. So if you can either make the concrete stronger, that is, if you're increasing the grade of concrete, then you can get a harder concrete. But the better or the more effective way to do to harden the abrasive layer is to improve the hardness of just the top layer. That's good enough most of the times. And a hardener, as the name suggests, is the layer that goes on top of the concrete floor that improves the abrasion resistance of the top layer. So this is the fundamental of what hardener is about. How do we specify hardener now? Most of our hardener specification today is to do with kilograms per square meter of specification. So when we have a hardener, we specify kilogram per square meter. We usually specify brands or a name, product names. We specify kilograms per square meter. But the problem is we are mostly stuck with a dry shake method, particularly when we have a vacuum dewatering. When we try to suck out the water using a vacuum dewatering process, the fundamental that we need to understand is these cementitious hardeners, when using a dry shake method, depend on the water available as a bleed on top of the concrete surface to hydrate. So this water is needed for the hardener, whereas during doing a vacuum dewatering, you are trying to remove this water away from the surface. So basically, you can safely assume that vacuum dewatering is not a very compatible method when it comes to the dry shake hardener. Hardener delamination becomes a very common problem. If you have incompatible systems, if these hardeners don't have enough water to adhere to the surface, then this is a very common problem. You may have seen this. This is called delamination of the hardener layer. So because of the fear of delamination, we are hence forced to move to lower and lower dosages of hardener. So we are now starting to even talk about 2.5, 3 kilos of hardener, which is not even 1 millimeter of thickness, which is very, very low. So typically, because the surface, the thickness of the hardener layer is going down, the durability of the surface also becomes a question. Particularly when you have intense traffic in a warehouse scenario, you will have issues like this when the top layer is just lost to continuous abrasion that's happening on the floor. So as a conclusion, you can say that the right way to specify a hardener is to identify the type of usage of the floor and then decide on the thickness of the hardener layer depending on the durability that you would expect. So when it comes to how we choose a hardener, it's important that the aggregate grading in the hardener is uniform. There is adequate hardness that a hardener layer imparts. Hardness is of course obtained from the aggregate that's used in manufacturing the hardener. So when you have just a simple comparison between a soft aggregate that is something like a talc, you can see that if you have a talc aggregate, you can scratch it with your nail and you will be able to form indentation on the aggregate. So if you move to harder and harder aggregates, you can move from quartz and then even up to emery and corundum. With a corundum, you can see that even if you have a masonry drill bit, you will only start to have indentation with a masonry drill bit when it comes to corundum aggregate. So that's just to give you a analogy of how hardness is obtained by using the aggregates. Then of course there are additives that are dispersants that give you excellent spread of hardener, and then of course the shrinkage control that can be imparted on the hardener layer, and you can have color. So gone are the days when people are choosing just gray colored cementitious hardeners. People have started to choose color for a hardener, and you can get beautiful colors using hardener. And of course the layer thickness is an important parameter when it comes to finally assessing the durability of a hardener layer. So layer thickness is very important to give you durability for the hardener surface. When it comes to how we specify hardener, which is the right way to specify hardener thickness is based on durability. Like I said, that's only kilograms per square meter, but that's the only thing that kilograms per square meter can give you, thickness. Now talking about the abrasion class, depending on what vehicles or what kind of equipment that you are moving on the floor, you need to decide the abrasion class. Just going to the coming from the previous slide, you can see that if the aggregate in the hardener becomes harder and harder, the indentation that you can get is much lower. So with a standard test, the indentation, if it's low, it's classified as AR 0.5, and that's a better performing hardener. That's a more abrasion resistant hardener. So if you move from AR3 to say AR 0.5, you are increasing the grade of hardener, and you can choose different kinds of hardeners based on the class of hardener, and hence this forms the right specification for how we have to specify hardener based on the abrasion resistance, and this is the right way to specify hardener. What is the right way to apply a hardener? Now we spoke about how to choose a hardener. Now when we want to apply the hardener that we've chosen. The first and the most easiest method is, of course, the dry shake method and manual broadcasting. When we broadcast using a spade or something, hardener is broadcast manually on the surface. This is a semi-mechanical process, of course, where you can spread the hardener using these semi-mechanical spreaders. The best way, if you're using hardener in a dry shake method, is of course use mechanical hardeners, fully automated mechanical hardener spreader. These equipments are prohibitively expensive. They're not available in India yet. But if you are using these equipments to dispense your hardener, you can dose really good amounts of hardeners, say even up to a thickness of 3-4 millimeters, which is about 7-8 kilos of hardener. So it's possible because you are entering, you are starting to broadcast the hardener much earlier. In the first two methods, you are forced to broadcast the hardener only when you are able to start working on, start able to walk on the concrete. So that's a disadvantage with the manual methods, but with, of course, the with the mechanical hardener spreader, that disadvantage vanishes. But we should realize that there are no such equipments available in India. The other method which enables higher thickness of hardener layer to be used is, of course, the fresh on fresh method. There are certain hardeners that are manufactured tailor-made to such application methods. So these hardeners are applied as slurry. These hardeners are mixed as a slurry form and applied on top of the fresh concrete. So you follow it up with power troweling exactly the way you do for a dry shake hardener. But this is an alternate method for application of hardener, and you can go for a really thicker layer of hardener, or you can even increase the dosage, like so to speak. So by doing a fresh on fresh method, say for example, you can obtain even uniform colors on hardener surface. So you can, now sky's the limit. You can choose any color that you like. You can use a fresh on fresh application to dose a really thick layer, and hence a much more consistent color can be achieved. And add polishing to it. You can imagine anything that you want to do with a hardener, and you can get really attractive aesthetic performance as well from these hardeners. So this is just to give you an example of what is possible with hardener. Just remember, in these hardeners, it's not just about the aesthetic performance, it's also about the abrasion performance. So you can choose hardeners to suit for aesthetic look that you're looking for, as well as combine it with the performance that you're expecting from it from abrasion resistance point of view. So just to go on to conclude this point with liquid densifiers, many times liquid densifiers are also referred to as hardeners. Just to clarify, liquid densifiers are silicates, mostly of potassium or lithium, and they fix the free lime on the concrete surface. Hence, when they fix the free lime on the concrete surface, they densify the concrete surface. So it's pretty much like what a varnish does to wood. It densifies the surface of the wood. The same way, silicates densify the surface of the concrete. It has very little or no effect in improving abrasion resistance. Of course, there is a substantial improvement in the dust-proof performance. There is, of course, the added benefit of the gloss and the aesthetic performance. But this is not necessarily to do with increase of abrasion resistance. This is not the purpose of densifiers. This is the clear difference between what hardeners and densifiers do. Liquid hardeners are not a replacement to dry shake or powder or cementitious based hardeners. So these are two different systems. They can be used with each other. They are very compatible with each other, but they cannot be used in place of one another. So this is very clear. And moving on to the last material that we wanted to talk today about sealants. Sealant is a very interesting subject. Many times sealant is understood or misunderstood that it provides better hygiene, and that's the only thing sealant does. But it has to be understood that sealant also plays an important role of protecting the edge of these joints. So when there is a sealant that's flush with the surface, it also helps in providing a a protection to these edges. So this is what a sealant does. So an unprotected joint like this is bound to get damaged from traffic. So you protect it with sealant that looks like this. So now going on to what sealants do or what sealants have as a property. There are two important properties of sealant. One is, of course, the hardness. Usually it's noted by a Shore hardness of the sealant. The second important property of the sealant is its flexibility. So sealant, it's important to note that the sealant has both these properties, and sealant has to have a combination of both these properties. And the most intriguing part in these two properties of sealant is that they are conflicting properties. And again, restating the same fact, you need to understand that you need both. You can't have an extremely hard sealant and compromise on the flexibility, or vice versa. So this is what this is just to explain what sealant, what the wheels do to these joints. They move across the joints and they break the joints if they are not protected with sealant. So what do sealants do? If the, like I said, if there is no protection, it is bound, the joints are bound to break. What does a sealant do? It protects the edge of the joints, just like this. When wheels move across, they transfer the load, or they absorb the shock, and they don't allow for the joint edges to break. Which sealant is suitable? It's a very tricky question. There is no one answer, one clear answer to this question. Which sealant is suitable? The answer is higher movement accommodation factor or highly elastomeric sealants are suitable for early application. The harder the sealant is, it's much more suitable for later applications. So different choices of chemistries, of course, available: polysulfides, epoxy, and polyurethanes. Polysulfides are perhaps a generation old, and they are among the most common kind of sealants, but they're not the most advantageous. Just to summarize or capture what we have been talking about sealants in a tabular format. So, like I said, the flexibility and the hardness are conflicting properties, and you would require a flexible sealant for an early application and a harder sealant for a later application. So polysulfides typically fall into the first category, and polysulfides many times don't have enough hardness so that it cannot be used in highly trafficked areas. When you use polysulfide sealants in very high trafficked areas, then you could have raveling of these sealants or removal of these sealants in some form. So it's very important that the choice of sealant is correct, and typically polyurethane sealants are both flexible and hard. So at the same time, epoxy or semi-rigid epoxy based sealants have very low elastomeric property, but they are quite rigid when it comes to application. So these are suitable for much later application. Thank you very much. This is what I wanted to talk about, all these four materials. Let's go back to Dr. Vish for questions from the entire event. Thank you, everyone.
Thanks, Rama. Again, apologies to a lot of people who gave their comments on not being able to see the presentation. I read through all the chat after my presentation was over, so apologies. But again, if you have any questions, then this is the forum. You've got Piyush and Rama, who are experts on floor. If you have any questions on concrete, then I can field it. Please go ahead.
Yeah.
So Rama, how are we doing it? Are we going to go through the
If you have
chat
already,
and take
yeah,
questions?
you have already
Okay.
compiled some questions. Seeing the chat, you have already compiled some
Yeah.
questions for each of us, right?
Yeah.
So you can start
Yes.
with them.
So I can start with those. Let me pull that up. So let me start with Piyush and Rama, and then I come to myself. Rama, why do we need a slip membrane if there's a PCC layer below the floor? Can you clarify this?
Yeah. Okay. So when we spoke about slip membrane, I had a point that I added that you need to have a slip membrane whether you have PCC or a lean concrete or not. The reason is the concrete that you are going to cast as a floor is bound to shrink. So you need to make sure the layer that's just below the concrete floor allows for the concrete to shrink without a restraint. If you don't have a restraint free bottom of the concrete slab, you could have issues related to restraint and hence cracking. So it's very important whether you have a PCC or you don't have a PCC, you should essentially have a layer just below the concrete that allows for slip. So that's the LDP sheet or the slip membrane that we're talking about.
Thank you. Piyush, a question for you. What is FM2? What does it signify?
Okay, so FM2 is kind of a floor that is used essentially in warehouse applications, and what it means is it refers to the levelness and flatness of a floor. There are certain requirements in terms of tolerances. Uh, there are two properties, property E and property F. I would not go into the technical details, but in terms of the user requirements, if your rack height is anywhere between 8 meters to 13 meters, that is what you would specify for a reach truck without side shift. So in one line, it pertains to levelness and flatness of the floor. It has nothing to do with the strength or any other parameter.
Okay, thank you. While we have you with us, why do you insist on a 150 slump? Why not a 100 slump?
Okay, so 100 slump would be very challenging for several reasons. First thing is the men would definitely struggle because if the guys saw the photos carefully, we do about 6,000 square feet, 7,000 square feet a day. There's a lot of pulling involved. Secondly, the equipment also would struggle. Laser screeds typically work very comfortably at 150. 120 is still okay. 100 is something uh, they would struggle. And apart from that, our finishing window would reduce tremendously at a 100 slump. We do need that time for our operations to run in a controlled manner. And secondly, why? So, secondly, if I am saying I am able to run my operations at 125, why am I asking for 150? So, if people are following my presentation carefully, that is what I was saying. I need that for contingencies. Things can go wrong at site, trucks might not turn up, slumps might vary. So, that is what I need to work comfortably and consistently day after day.
Okay,
Thank you.
there was a question for me. Which admixtures are commonly used in concrete? Well, uh, there are many types of admixtures, but the most commonly used are called dispersants or water reducers. They basically help uh, make concrete flow better at a lower water to binder ratio, at a lower water ratio. Yeah, so that's the most common admixture used. Um, Question again for Rama. Uh, our consultant has specified a polysulfide sealant. Is it okay for a warehouse?
Yeah,
What do
this
you
is
think?
a very common question that we see. Polysulfide is one of the first kinds of sealants that was ever used. That this was I think a couple of generations back. This was the first kinds of sealants that were used in a warehouse floor. It's a couple of generations old. These are not very suitable for high traffic. It's a very elastomeric sealant. It's not hard enough, so it's not very suitable for a very high traffic. More suitable sealants for higher traffic would still be something like polyurethane sealant. So polysulfides may not be the best chemistry available in today's world. Yeah.
Okay. One more question for you, Rama. Are liquid silicate floor hardener, do they cure as well as what's claimed by many companies?
Okay, so it's not true because curing is a process where you're forming a kind of a film. So any curing membrane that you would look out for is essentially film forming. So curing membranes are a liquid. They form a film on the surface of the concrete, hence prevent water from leaving the concrete surface and hence curing the concrete. So this is the performance or the behavior of a curing compound. When it comes to silicates, the first thing is, for the silicates to work, you will need the primary hydration in concrete to start already. So you would not typically apply these silicates in early phases of concrete. You would need the concrete to hydrate a little bit, to react a little bit, to harden, and then for the free lime to be fixed, you need to add these silicates much later. So curing is done, even the time that you do curing and the time at which you apply these liquid densifiers are different. Curing you would like to do the next day after finishing. So curing is, these densifiers come in much later. So it's impossible to look at both these performance parameters together. So it's impossible for me to think of both these properties being achieved by one chemical.
Mhm.
Yes, Dr. Vish.
Okay. One question for Piyush. During pouring on site, if we get lower slump, what to do?
There are several things you can do. You definitely you can add admixture. It depends how low the slump is. If it is like beyond the limit that you have set for rejection, it needs to be rejected outright. But if it is on the borderline, you can add admixture along with water and bring it to the required slump. You never add just water. You need to redose it, or correct it with admixture. Thank you.
Okay. Thank you. Let me take a couple of questions that came for me. Um, CSH particles, what kind of chemicals can we use to accelerate the formation of CSH particles? So typically the chemicals are either nuclei of CSH that can form the place where other CSH can grow and accelerate growth, or you can use traditional accelerators like calcium nitrates, and these typically will also help increase the CSH growth early ages. But be careful about later age strengths when you do that. Another question for me was, which is better, PPC or OPC? Well, you can use both. Yeah. What is most important is whether they meet your concrete uh, specifications in terms of both handling as well as durability. If they meet those specifications, then yes, you can use both. Let me then ask a question for Rama. What is the cause of delamination and how can we avoid this?
Okay. Delamination is basically a process where you have some material on the surface that you lose. It can happen immediately after casting the floor, or you can have it during the service of the floor. Many times it happens because when you have, you could have a hardener or you don't have a hardener and you can still have delamination. Typically when it happens, when a hardener is being used, there is lack of adhesion of the hardener layer to the concrete. like we said like I said during the presentation, the hardener is a cementitious material, and it depends when it's supplied on a dry shake method. It depends on the bleed water that's available, and this bleed water is necessary for this cementitious.
Excuse me.
So this bleed water is essential for the cementitious hardener for it to hydrate. So if this is inadequate, or the finishing process is too delayed, or the hardener dosage is much more than the availability of the bleed water, you could have insufficient or incomplete hydration of the top layer, and hence you could have delamination. So this is one of the primary reasons for delamination. The other reasons could be delayed hydration of concrete, delayed application of hardener itself, or deleterious materials that could be on the surface of the concrete when applying hardeners, that could prevent for the hardener layer to adhere very well on the concrete surface. The good some good ways to mitigate delamination issues is to choose the right kind of hardener, to maintain adequate amount of bleed and match the amount of hardener that you're applying with the bleed, or to use hardener in the form of a slurry. Good tooling helps in uniform distribution of the bleed water, and then you can perhaps use a hardener in the form of a slurry So you are no more depending on the bleed water from the concrete, and hence you have a hardener layer that's independent of the bleed water, and hence you don't have delamination. So this is also another way to mitigate delamination issues.
So there's a question, Rama, how to repair if a floor gets delaminated?
It depends on the extent of delamination. Mostly, if delamination is just a small patch, removal of the top patch is important. And when you are doing a patch repair and delamination, the two things that you need to remember is one, there is going to be a color difference. So it's not possible to repair a delamination patch by using some material. Even if it's using the same material, you will still see the color difference in terms of a patch. Second is, when you're doing a repair, it's very important to also identify other areas which have not come off, but they are not. You could do a sound test by using a small reinforcement rod, or pulling around a heavy chain across the floor, to see if there are other areas of the floor that have some extent of delamination that's not come off, but it's still weak and it's going to come off in some way. Patch repair and complete replacement is needed when you have huge amount of delamination that is covering the entire area of the floor. Yes, Dr. Vish.
Okay, there's another question by Singaram. Hi, Rama and Piyush. In general, flooring concrete is done inside the shed. In that case, what is the expected shrinkage? And if we use fibers, is it possible to reduce the cracks?
Piyush?
Rama, do you want? Okay.
Yeah, I'll go. Yeah.
Okay.
So the thing is, industrial floors in the true sense are necessarily done indoors. So you prevent any interference of heat or rain from above, and interference of wind from sideways. So typically industrial floors are done indoors. That's the best practice. So when you do this, you are mitigating external factors as high temperature differential and high amount of interference of the wind, which contributes to high amount of shrinkage, because it aids fast evaporation of water. This is one. Usage of fibers, say synthetic microfibers or glass fibers, helps in the early phase. You're talking about still the area of plastic shrinkage when the concrete is still hardening. So you could have effective contribution of these synthetic fibers and glass fibers. When it comes to later age, they don't have much of a role. So maybe steel fibers do help, but still, when it comes to shrinkage, it has to be controlled by using good detailing practices, like usage of isolation joints to isolate the other elements, to make sure we are creating a good slip membrane to avoid friction, and then to take care of the detailing aspects, such as creating the groove to make sure that the concrete, when it shrinks the way we want it to shrink. So that's very important.
Mhm.
So these are some ways to mitigate uh, shrinkage. I hope I've been able to answer the question, but we can. Yes, Dr. Vish.
This is for Piyush. The practitioner has got a major role in doing the floor. How is the ground force, and I'm guessing this means people, how are they being trained to do these jobs?
So, I mean, best way to learn it too is to be be on the. It's like on the job training. This is highly skilled work, uh, which requires specialized techniques, and that is kind of, I would say, is passed on down from one person to the other person, and there is some amount of possibilities of training available. A person like Rama, who's a expert and a flooring consultant, can do that for a lot of people. But a majority is just information handed down from one person to the other, from the senior guy to the junior guy, and communication is very important. Like, I as an engineer understand certain things, so I should have the ability to communicate it to my guys in their own language, so that they understand what bleed is. And I can't just explain to them bleed water. I have to be able to talk to them in their own language. So that is an important skill to have.
Mhm.
I don't know if I've been able to
Yeah,
answer the question, but this
Yep.
is what it is.
yeah, I think. Perfect, Piyush.
Okay, then there's another question about reinforcement. Why two layers of reinforcement when we had good floors working well, even for heavy industries. This will be the first question from the client. Why use two layers of reinforcement?
Okay, so basically, like I explained, I'm extremely sorry that this graphic was not there when I explained this, and we had to move on and complete the presentation anyway. So I will like to bring your attention that when you have two layers of mesh in a floor, the top layer of mesh is only for shrinkage. So we know from the basic principles of concrete that when you have a stress, then you have a neutral axis. And when you have a neutral axis in a floor, which is a ground supported system, the tension is on the bottom. And that's where you need to have reinforcement when you are mitigating the moment. So what is above the neutral axis, and this goes without saying that if you have a reinforcement layer somewhere in the middle, it does nothing because it's on the neutral axis and there is absolutely nothing that reinforcement can do. So on the top is of course the layer where you have shrinkage in concrete. So that's the shrinkage reinforcement that you would add on top. So like I said, you can choose to have just one layer. If you choose to have one layer, you need to identify the position, and that's very important from design point of view. That if you identify the position to be the top layer, then it means that you don't want a moment reinforcement here. So it means that you are taking care of the moment with just the thickness of concrete. We have numerous hundreds and thousands of kilometers of roads that are done without any reinforcement at all. So these work perfectly. So you need only thing you need to make sure is you need to make sure the concrete is thick enough to take the moment by virtue of the concrete itself, by the performance of the concrete itself. So the top layer is for shrinkage and the bottom layer is for mesh. If you choose one layer of mesh and you want to put it in the bottom, it means that you are taking a conscious decision that any shrinkage that's happening is going to be controlled or going to be managed by you by careful detailing. So careful detailing assumes a lot of things that goes into a very long discussion. I don't want to take that. So basically, the fact is, if you are putting a reinforcement, you need to decide the position, and the top layer is for shrinkage, and the bottom layer is for moment. And please don't put it anywhere else. It has to be either in the top or bottom. And if you want
Thank you.
to contribute to both, have one at the top and the bottom. Sorry. Yes, sir.
Okay. I'll take one question that came for me, which was what's the difference between naphthalene sulfonate BNS and PC admixtures? And which one's better for the floor concrete? Well, PCEs are typically better. Um, Both BNS and PCEs can be used for concrete, there's no problem. However, PCE gives you a lot more flexibility in terms of control of things like setting time, as well strength gain, as well as of concrete. So typically, you can do much more with PCE than a BNS admixture. Another question that came from Naveen: floor densification, colloidal silica better than lithium silicate? Question.
Okay, I guess I covered this topic, so I take this. So, colloidal silica is uh, another form of chemical that can fix the lime on the concrete. So you can have different silicates, that is a potassium silicate or a lithium silicate or any silicate, or you can have colloidal form of silica. It's just a medium to transport these silicates and make sure that they react with the lime that's available on the surface. So it's pretty simple. So it depends on a lot of other conditions, which one is effective. And colloidal silica, of course, by virtue of the chemistry itself, it's quite reactive, much more reactive than in a salt form. So in salt form, you would of course have potassium or lithium silicate, which have slightly reduced reactivity. The reactivity is slightly higher when it comes to colloidal silica, but it doesn't mean that one form of silicate is definitely advantageous over another. It depends on where you're using it and how you're using it, and it depends on on the way you're following it up with the polishing as well. So, and the durability that you would expect from this. So it doesn't mean, just to capture it in a nutshell, it doesn't mean one is better over the other, but definitely there is a difference in the reactivity. And colloidal silica is the highest, lithium silicate is is perhaps the next, and potassium seepage is slightly lower.
Thank you. Question for Piyush: how to manage slopes when concreting for food industries?
Okay. Yeah. I know there are a lot of drains that you need in food industries. It is difficult to, kind of answer this without a pen and a paper, or it just, you could use laser levels to do your spot checks. There's a certain way that you need to fix forms. What is most effective is something called as a temporary formwork, where so let's say, so in a food industry, what happens is you have a square shape at the bottom, like uh, it's like a havan kund, to people who understand what havan kund is. So the four walls of that havan kund, you can shutter independent of the other, put concrete, screed it, and when that concrete of that part is in an advanced stage of setting, you de-shutter it, you remove the temporary formwork, and this is how you build all those four slopes. This is one technique. There could be other ways of doing it. It's very specific to the requirement.
Okay, there are a lot of questions on industrial floors. Uh, let's see. Okay, how bad is the heat of hydration for massive volumes of concrete being poured into industrial floor? How does a practitioner tackle with this problem?
Piyush, you want me to take that?
Yeah, I mean, I don't think heat of hydration is a significant concern. I think Dr. Vish can also add in here, because we are dealing with a very high surface area kind of a situation. What I have noticed is, uh, in several sites, I noted the temperature at which the concrete came in, and I noted the temperature half an hour after it was poured. So the temperature actually was lower, about 3 to 4 degrees lower than what it came in. It just uh, it just tells me that the atmosphere is helping the concrete cool down. I really don't think you know it is different from a dam application or a mass concrete application. That would be my answer. Dr. Vish, do you want to add something to it?
Yeah, I mean, basically, you're looking at a very high surface area compared to the depth. So, I would not expect serious differences in concrete temperature between the core or any part of concrete and the surfaces. So, I think the chances are pretty low. But if you are engaging in anything special which has at least 2 meter by 2 meter kind of element, then one needs to do the due diligence study before you do place any concrete like that. There's another question, and I don't know who can, which of you will be able to answer this. So I open it up to both of you. In northeastern part of India, flooring work is very challenging because water table is very high, and leakages are a very big problem. Sometimes floor are always wet. How to protect from the same?
Okay.
There's
So
Yeah,
go
Rama,
ahead.
go
Go
ahead.
ahead, Piyush. Go ahead. Go ahead, Piyush.
So I think in terms of, I'll talk from a perspective of sub base. One thing that you could definitely do is, in the choice of material, have a free draining material. Definitely non-expansive, so that if there is fluctuation of water table, it is able to absorb it and drain it as quickly as possible. So what I'm saying is, you need to apply mind in using the material for your sub base as well as subgrade. And I think Rama might have something to talk about HDP and LDP. Is that what you want to
Yeah.
mention, Rama?
Yeah.
Please.
Yeah. Sometimes HDP is thought of as being a bit more impermeable when it comes to the capillary rise of water from low, very high water table on the subbase, but it's very difficult to use HDPE because it's basically a harder material, and it's very difficult to get a flat surface to get a restraint free slip membrane. So HDPE may fail from the point of view of a slip membrane, but it may slightly perform in a vapor retarding scenario. The best way to tackle this is to increase the thickness of the LDPE sheet that you use, with maybe increase the number of layers of LDPE sheet used, with perhaps some overlap between these layers, so that there is mitigation of capillary rise in these scenarios. Dr. Vish, maybe we should take one or two further questions. I think we have reached the,
To that point. Okay.
although there are,
I'll
although,
take. Yeah, I'll take. Actually, there are two questions that are related. So one question was, what's the recent technology invention in concrete? And the second question that I wanted to relate to is there an admixture for geopolymers? And the answer is yes. There are dispersants that are now available for geopolymeric concrete. So whatever we can do with concrete, we can start to do many of those things with geopolymeric material. Then one last question. Let me see. I'm quickly going through the. Okay, do we need to go for epoxy or PU coatings for long life? Is it necessary or optional?
yeah, Piyush, you,
It basically depends on the application. Rama, you can add further, but I mean, some flows don't need some flows need it as like something like a food industry or a pharma industry needs a coating as a norm, but a warehouse does not necessarily need a coating. Rama, you can expand further on this.
yeah. So when it comes to cementitious materials, you have to understand cementitious systems are highly alkaline. So if you're talking about chemical exposure, when with respect to highly acidic materials like like you can say food industry, most of our contaminants are acidic in nature. So in a food industry, like Piyush rightly pointed out, anything acidic on a concrete surface is not going to help, is not going to be taken by concrete. So you can have a lot of pitting happening on the concrete surface if you have acidic exposure. So you have to look at it objectively. If the question is only about aesthetics and dust proofing, you can have very good hardeners and very good densifiers and polish the concrete, and you can have a dust free surface. If it's only, and you can even have color in a cementitious system. Second, if you're talking about chemical exposure and chemical resistance, of course you need elements such as polyurethane or polyurethane concrete or epoxy coatings on top of the concrete, because concrete is not resistant to acids. Third, if you're looking at aspects that are related to compliance when it comes to electrostatic discharge or things like that, then again you will need synthetic toppings on top, so that you can take care of dissipation of these charges through the topping systems, and hence the things that concrete can't do. That there you may need a topping, but it's not always the case. It should not be viewed as if an epoxy or a polyurethane topping is just to increase the durability of concrete. It has to be objectively seen why you need it, and you have to choose whether you need it or not. Yes.
Okay, there's still a huge number of questions, and I think we won't be able to answer all of them at this point of time. Uh, but I think we can even take these questions offline if needed. But I want to thank both of you, Piyush, Rama, and also the audience, and for so many questions and such a lot of interest. It's absolutely nice to see this. Again, apologies for the network issues that we had off and on. Um, but other than that, over to you, Rama, for conclusions.
Yeah. Thank you very much, Dr. Vish, to have accepted our invitation to be our expert speaker on concrete. And there are so many things about concrete that you can talk about, but this is a very limited domain. And thank you very much for adding so much value to our presentation. And
Yeah.
looking forward to, and thank you, Piyush, and thank you, Dr. Vish. And perhaps we'll meet in another forum. And thank you, everyone, for being a patient
Thank you.
audience.
Thank you, everyone, for your patience and time.
Thank
Really
you, everyone.
appreciate it. Thank you. Bye. Take
Take
care.
care. Bye.
Take care.